Okay, so for the last two examples, I wanted to show you example 4 because what we notice is that we've got a polynomial function with t and then a trig function with the cosecant squared. So our first instinct might be to use tabular. So I want to show you why the tabular doesn't work when you have something other than sine and cosine. So let's pretend that we didn't realize it wasn't going to work, and we began by making the columns for u and dv, and you put the polynomial in there, and then the derivative of t is 1, and then the derivative of 1 is 0, because t is basically just like x. And then for dv, we would put the cosecant squared t, and see now we have to do antiderivatives, and we do have an antiderivative for cosecant squared. The antiderivative for cosecant squared would be negative cotan of t, but we don't have a known antiderivative for cotan of t. So there's no known antiderivative for cotan of t. Or actually there is. There you can find it, it's just not a formula for it. You would have to use u substitution. So because of that, u substitution, because of that, the tabular method sort of fails. It works really nicely when you can just find the antiderivatives easily, but if the antiderivative, there's no known formula for it, you have to use a u substitution, well, then it's a little bit harder. So you might as well just use the long form of integration by parts. So we'll cross out the tabular, and we'll go ahead and just do this the long way. So the long way would be step 1. I'm going to determine my u and my du, and then my dv and my v. So u is t, and then du would be 1 dt. dv is cosecant squared, so v would be negative cotan t, and then, oh yeah, sorry, the dt was right there. Negative cotan t. So then step 2 would be the uv minus integral v du. So uv is just negative t cotan t minus the integral of negative cotan t times 1 dt. Well, this negative, I can pull this negative out and cancel these. So I have negative t cotan, oh sorry, I wrote cosine, that's cotan. Negative t cotan t plus integral of cotan t dt. Well, now I have to find the integral of cotan t dt, which I can find. I just have to use a little u substitution. So how about we do that on the side over here? Well, first of all, let me rewrite this. I have negative t cotan t plus the integral of cosine divided by sine. So you have to use first an identity, the quotient identity, which says cotan is just cosine divided by sine. And then I need to use a u substitution. So let's look up here for the work. So I'm going to let u be the denominator. And then du would be the derivative of sine, which is cosine t, and then dt. So then dt is equal to du divided by cosine t. Okay, so what I can do is I can rewrite this integral. So I have negative t cotan t plus the integral of cosine t divided by u times du, which is times dt, excuse me, which is du divided by cosine t. The cosine t's cancel out. And so I end up with negative t cotan t plus the integral of 1 over u du. And this is really easy to find the antiderivative of because we have a formula for it. The formula of antiderivative of 1 over u is ln of u. So then this is equal to negative t cotan t plus ln of the absolute value of u, and then of course plus a constant. And then I just have to resubstitute the sine of t back in here for u. So this just has to be put back in there. And then I'm done. So my final answer would be negative t cotan t plus the ln of the absolute value of sine t and then plus a constant. So this integration by parts involved a little bit more work because once we got to the cotangent, we had to rewrite that as cosine over sine and use a u substitution to evaluate that integral. So this problem here required both integration by parts and u substitution. And something to be careful of is like the u from integration by parts is not the same thing as our u by u substitution. So we have to be able to keep everything straight. And then eventually we ended up at our correct answer. So that's definitely on the more challenging side. Okay, and then last but not least, we have example 5, which is like my favorite because it's super fancy. I love getting fancy in math. This is one of those problems that if someone had never showed me how to do this, I would never be able to figure this out on my own. But now that I've seen how to do it, you know, of course I remember how to do it. But I love the fact that, you know, it's not so obvious. Like someone has to show you how to do these. And I think it's really cool. Okay, so anyways, what we have here is like the worst case scenario, so to speak, according to Lippitt, for integration by parts. I've got an exponential function times a trig function. And if you recall our Lippitt, those are like the last two. Those are like the bottom of the barrel. They're the hardest ones to work with a u substitution. So it requires getting fancy. Okay, so here's what we're going to do. In the order of Lippitt, exponential comes before trig. So I'm going to let the exponential one be the u, and then I'll let the trig one be the dv. So u is going to be e to the negative y, and then du would be negative e to the negative y, dy. Okay, and then v is going to equal cosine y dy. And don't let the y's throw you, by the way. That's just another variable. You can treat it as if it were x. Okay, so dv would be sine y because the antiderivative of cosine is sine, and when you take the antiderivative, the dy goes away. Okay, so now I'm going to do uv minus integral v du. So I get e to the negative y times sine y minus the integral of v du. Sorry. Oh, wait. Sorry. I screwed this up. This should be dv right here. My bad. I apologize for the confusion. This should be the dv because this is like the derivative of something, and then v is the antiderivative of dv. I apologize for that. So the integral of v du. So this should be e to the negative y sine y dy. Okay, so, oh wait, v du, so this should be negative. So it's v du, so it's negative e to the negative y times sine y and then dy. So you get something that looks almost identical to the original, and you might even be wondering, am I always going to end up with e to the y, either cosine or sine? And the answer is yes. These are going to go back and forth. So I'm going to do an integration by parts one more time, and then I'm going to show you how to get fancy. Okay, first let me simplify these negatives a little bit. So I have e to the negative y sine y plus integral e to the negative y sine y dy. So I need to do integration by parts all over again. So again, I have my u and then my dv. So let's go over here. So u is going to equal e to the negative y. So du again is negative e to the negative y dy. dv is going to be sine y dy. So v, which is the antiderivative of sine, is negative cosine y. And then I have to put it all together. So I've got the uv from before. So I have e to the negative y sine y. And then I have to turn this into uv minus v du. So I have plus uv, which is e to the negative y times negative cosine y, minus v du. And these negatives are going to cancel, so it's e to the negative y cosine y dy. Okay, so you're noticing it's going back and forth. It started with e to the negative y cosine y, became e to the negative y sine y. Now it's back to being e to the negative y cosine y. So here's where you get fancy. This whole thing right here is what this integral is equal to. So this integral, I've split it up now twice into uv minus v du, and then again uv minus v du. So here's how we're going to write it. We're going to say this integral, the integral of e to the negative y cosine y dy, is equal to all of this and that's a true statement because I used the integration by parts to split this integral up into these three parts. So this integral is equal to all of this. Well, I don't know if you've noticed it right away, but we've got a couple of like terms, believe it or not. These two, which, by the way, is what I'm trying to solve for, are like terms. So what I'm about to do is I'm about to add this one to both sides. And because I'm out of room, I'm going to bring this over to the back side of the page. And I'm going to rewrite it so you can see it happen. So what we observed is that the integral of e to the negative y cosine y dy is equal to, let me see what I had, e to the negative y sine y minus e to the negative y cosine y minus, the integral of e to the negative y cosine y dy. And so we recognize that these are like terms, so I'm going to go ahead and add it to the other side. So it'll cancel from that side. And then on this side, I'm going to have 2 of the same integral. So I have 2 times the integral of e to the negative y cosine y dy. And then that is equal to e to the negative y sine y minus e to the negative y cosine y. Now I'm going to go ahead and just divide both sides by 2. And then I have integral e to the negative y cosine y dy is equal to e to the negative y sine y minus e to the negative y cosine y divided by 2. And that's pretty much our answer. Oh, plus a constant. Because I was trying to solve for this integral all along, and so now I have a statement that's saying this integral is equal to this. So this is what it must be equal to. And I'll just simplify that a little bit. So it's basically 1/2 e to the negative y times sine y minus cosine y. So I basically was able to factor out an e to the negative y over 2 from both terms. And then, of course, plus a constant. So that's how I call getting fancy with it, is because with the other problems, we didn't have to set up this equation because we were able to just keep following the uv minus v du process until we got to an answer. But that was never going to happen here. So we followed the uv minus v du process until we got an identical integral to the first one. And then we set up an equation using the first integral and the 3 pieces we got, where these are like terms, and then you combine the like integrals together and you end up with a constant multiple times the integral that you can just divide. And that is how we arrive at our answer. Okay, so that's pretty much how all the questions are on your extra credit worksheet. I have attached the worksheet along with the outline for these notes. Each question you have an opportunity of 2 points for accuracy, and it is I will decide when it's going to be due, and I will announce that in class. So best of luck to you.